Okay, so let me get started. Yeah, so today I'll start off again with a quick recap of everything we've seen so far, and then we'll jump in to the statistical optimal transport piece, which is today we'll talk about estimation of the transport map from samples. Okay, all right, so let me quickly recap. So where we were talking, we first formulated 2 lectures ago now, Monge's problem. So Monge's problem was to find a transport map, given a pair of distributions, find a transport map that minimizes the average cost of the transportation. And then we talked about Kantorowicz's problem, where rather than look for transport maps, we were looking for couplings between pairs of distributions or pairs of random variables. And then we said, try to find the minimum cost coupling. We remarked that this Kantorovich formulation, it's a nice linear program, has lots of nice structure to it. Then we talked about Brennier's theorem, which kind of gives us at least one of the connections between these two programs. We said if the first measure, mu, the source measure, is absolutely continuous, and your measures have two bounded moments, and you're working with the quadratic cost, then Monge's problem has a solution, and it is of the form that it's the gradient of a convex function. Also, Kantorowicz's program, which always has a solution which coincides with that of Monge's solutions, right? So there is a coupling which is of the form, it's the joint distribution of a pair of random variables, which looks like x and grad phi 0 of x, so x and t0 of x. And so the coupling and the map are very closely connected in this setting. We then talked about this polar factorization theorem, which just gave another way of motivating this optimal transport map as an object of interest. We said, under at least the conditions of Brennier's theorem, you can take any transport map, anything that moves mu onto nu, and decompose it into two pieces. One of them is, in fact, this optimal transport map for the quadratic cost, and the other is something which is measure preserving. So it doesn't help us with the goal of transporting. So there's one map S, which just moves mu onto itself. And then there's another map which kind of takes mu and pushes it to nu. And there's a canonical way every map can be decomposed in this way. And so it's an interesting target of inference in its own right. Even without mentioning the quadratic cost, you see that this optimal transport map for the quadratic cost pops out. We also talked about Wasserstein distances. So the cost of Kantorowicz's program, so the minimum cost coupling, so the cost of the minimum cost coupling defines a metric between distributions. In particular, if you use the cost, which is the Euclidean distance raised to the pth power, these are called Wasserstein distances. And then we started talking about duality. So this was lecture 2. We derived the general dual to Kantorowicz's linear program, and we saw that it has this form over here. It looks like maximize over a pair of functions f and g, which are sometimes called Kantorovich potentials. You maximize the expected value of f under mu plus g under nu, subject to a constraint that f plus g has to be less than the cost between the, so f of x plus g of y has to be upper bounded by the cost. So then we use this dual to gain some insight into the OT program. So particularly, we showed two very important facts. The first one was if you use the cost, which is the W1 cost, so that means it's just the Euclidean distance, not raised to any power. Then we used this dual plus some strong duality claim to show that the W1 distance between two measures, mu and nu, can be written as the supremum over one Lipschitz functions of the integral of f d mu minus the integral of f d nu. Right? So it has this dual representation, which shows that the W1 distance is in fact an integral probability metric. So it is the supremum over a class of functions of the expected value of the function under mu minus the expected value of the function under nu. For p equals 2, so this is the case where the cost is the Euclidean distance squared, we saw again you can use the same dual, partially optimize it in some way, and arrive at this other program that is related to the dual. It is sometimes called the semi-dual, which says, okay, something closely related to the dual is to find a function phi and which minimizes this expression, the integral of phi under mu plus the integral of its conjugate under nu. So where this conjugate is the usual Fenchel conjugate, it's defined over here. And this other property of the semi-dual that we didn't prove but said is true and will be useful for us is that if the conditions of Brennier's theorem hold, then the OT map can be related to the solution of the semidual. So if you find the function that minimizes the semidual, it will in fact be a convex function, and its gradient will give you the OT map. So then we jumped into this statistical optimal transport setting. So the statistical OT setting is, rather than hand you the distributions mu and nu and you investigate some properties of the OT map, we're going to say, I'm going to give you sample access to the two distributions. That is, you will obtain random samples from mu and nu. And what you want to do is to try to estimate something about in the OT world. So you could try to estimate the Wasserstein distance between the measures. You could try to estimate the transport map. You could try to estimate the measure under the Wasserstein distance. So this is some sort of density estimation task. Or you could try to estimate some sort of barycenter or midpoint between all of these distributions. So if I give you samples from a collection of distributions, you could say, what is the midpoint of all of these distributions? And these are all tasks that people have considered. So we will today focus on the first one. We talked in the last class about dual estimators. So dual estimators basically have this form. You, we know that if I optimized the semi-dual with and put in some mu and nu here, at least under some assumptions, I would recover phi zero, whose gradient will give me the OT map. And so this reminded us a little bit of the population risk and empirical risk minimization principle in machine learning. So where you say, okay, I want to optimize some population risk, what I'll do instead is optimize an empirical counterpart to it. The exact same principle here will tell you that a reasonable thing to do maybe is to compute phi hat, which minimizes now this function, where rather than stick in the population measures, which I don't know, I just stick in two empirical measures. And this gives me an estimate of the Brenier potential. So phi zero is sometimes called the Brenier potential. And instead, I'm going to get some estimate of this potential and maybe define my estimate of the transport map to be the gradient of that estimate of the potential. Okay. And maybe the main question for us was, what statistical properties does it have? Is there some sense in which, at least under some assumptions, t hat is close to the thing that I care about, which is t0? Okay. And before we start to answer that, let me define some other natural estimators of the OT map, and then we'll take it from there. Okay, so we'll talk a little bit about primal estimators now. So another thing that one could do um, is the following. So I've given you X samples and Y samples. So one thing you can do is compute what's called the in-sample coupling. Right? So what is the in-sample coupling? You should imagine I gave you some set of points from the source measure. This is, say, X1, X2, X3, and X4. And there are corresponding somewhere some points from the target measure. Maybe they look like this. So these are Y1, Y2, Y3, and Y4. So what I can do is compute the matching between these that minimizes the cost. This is just an LP, and there are reasonably fast algorithms to solve this problem. But what we'll do is compute some sort of matching. Maybe X1 goes to Y2, X3 goes to Y4. So it goes here. Right, so the first step maybe would be to compute an in-sample matching. And this we do by, so there are famous algorithms to do this. You can either use what's called the Hungarian algorithm, or there's something that Bertsikas came up with, which is called the auction algorithm. These are just ways of solving this LP somewhat quickly. So this is maybe just say solve Kantorovic's linear program, and you will get out a matching of the samples. This doesn't solve our statistical problem because we want an estimate ideally of the map everywhere. So even outside of the samples, we want an estimate of the map. So we have to come up with some way to extend so that I can generalize. If I gave you a new sample, where should I push it to? Right? So we want some sort of extension of this, maybe. And maybe one natural principle which one could use is to say, use the nearest neighbor principle. Okay, so what does that mean? If you want to estimate the transport map, one way is, so now I give you some new point. Let's say it's over here, right? You say, okay, I want to know what is t hat at some new point, let's say x new. I will just define it to be equal to t hat of one of my sample points, which is the nearest neighbor of the point x new. So in my picture, maybe this is the nearest neighbor. And so I will define the transport map at this point to be wherever x2 goes, which is over here. Okay. Does everyone roughly follow? So this gives me an extension of my transport map outside of my samples. I just use the nearest neighbor principle. I say if I want an estimate at some new point, I find its nearest neighbor and go wherever the matching tells me to go. Okay. So this, again, maybe one should ask, what statistical properties does it have? Is this a good estimator in any sense? And again, under the hood, there's this question of how do we even analyze estimators that look like this? Um, okay, so the other class of primal estimators is what I will call plug-in estimators. This is just a principle that maybe one could use to design estimators of the OT map, at least. Um, so what are plug-in estimators here? So we have samples x1 through xn from mu, and maybe we have some idea of how one might estimate a density, right? So this is some familiar task of density estimation. Statisticians have studied this for maybe 100 years now. And so one could say, okay, um, a natural thing to try to do is to just construct density estimates, uh, mu hat and nu hat. So we construct density estimates, mu hat and nu hat. You could use any principle you want. Maybe you could use a kernel density estimate. You could use, I don't know, your favorite other machine learning black box to try to design a density estimate. You could use wavelet estimators, anything you feel like. And okay, at least as long as mu hat is absolutely continuous, we know that there is a well-defined transport map from mu hat to nu hat. So maybe a reasonable estimate of the transport map would be to say, look at whatever is the OT map between mu hat and nu hat. Okay, so this could be a reasonable estimate of the transport map. And again, maybe one should ask the question, how do I analyze it? What properties does it have? Okay, so let me pause here. So I've sort of defined some estimators for us, and then we'll spend some time trying to think about how to analyze them today. Um, but before I do that, maybe are there any questions about the estimators that we've proposed?
For this OT map method, do you just solve the dual for your density estimates?
Uh, you could solve the dual, you could solve the primal. So, okay, this is like maybe one should say this is an in principle estimator. That is, you could say, yeah, solve the dual, solve the primal, anything you want. Both of them, because I assume mu hat is absolutely continuous, will lead you to the same t hat.
Got it.
So I have one question. So in the earlier principle, so wouldn't it be like better to use a smoother version of the nearest neighbors? Like maybe you express your given point as maybe some weighted combination using the Wasserstein distance or something. And don't know what maybe whatever the metric is, some metric weighted combination. And then you try to use the same combination on the other side.
Yeah, that's a very good question. It'll turn out, okay, we don't know any case where that improves, but it's primarily because you should contrast it with usual regression. So there's already noise in the matching. So in some sense, there's a lot of error in your original matching. You didn't exactly match X1 to the transport map at X1, you mapped it to some other point. And so because there's so much noise in the original matching, it doesn't make sense to further try to denoise in the second step. So maybe I'll say some high level thing. You should view, I don't know, this kind of OT map estimate as something like regression, but there's a lot of noise in what you decided to call the target. So we're in essence solving a regression problem from X to it's matching T of Y, but we don't know T of Y. So we're first using some algorithm to give us a guess and then trying to say, okay, we'll use some sort of regression principle on top of it. But the noise, the matching itself is so noisy that it turns out that at least we don't know any case where this using a cleverer estimator in the second stage helps. Does that make sense?
Just earlier, to be sure, when you're talking about the plugin estimators, what do you mean we can then either use? So I'm assuming this mu hat and nu hat both are some continuous densities that you've estimated.
Yeah.
And now, how do you use the primal here? Like primal, at least the method that we saw right now says, okay, you have n samples. Now you can do some sort of nearest neighbors, right?
Yeah. So that is one thing. So I'm just saying that, okay, so one way to try to compute this OT map would involve another level of discretization. So you could just say, I've constructed a density estimate mu hat. I could draw like some very large number of samples
Oh,
from
I
it.
see.
And then now uh, you do the same thing on the other one, and then you construct something like the nearest neighbor estimator on this very large sample discretization of it. So again, maybe you should, for now, just think of this as a in principle estimator. That is, it is a statistically valid thing to do. I can just define it to be this. If you wanted to actually compute this estimator, you might have to you have to be a bit clever about how you do it.
Got it. Thank you.
Okay. Any other questions? Okay. So then let me keep going. So maybe when we start thinking about analyzing these estimators, the first thing that one should ask is, what is the notion of quality that we care about, right? So this is called the risk in statistics. So it just says, if I gave you a candidate T hat, how would I know if I've done a good job or not? So you just have to put down some metric. And the one that people often use, which is somehow sensible, is to say, okay, if I give you T hat, I'll evaluate its quality maybe by its expected error. So that is, it looks like this. And I look at this quantity, right? So this is T hat itself is a function. T0 is also a function. So I look at the distance and their vector valued functions. So I take the difference, I take the norm, and I integrate it. So this is some sort of L2 risk measure. And maybe the goal is to say, construct for me an estimate T hat so that this risk measure is small. This is the way that we will choose to set this up. You could try to define other risk measures and try to analyze transport map estimation under these other loss functions, but this is the one we'll work with. Everyone okay so far? Okay, so now let me tell you briefly about what is the main thing that we're going to do. At a high level, all of what we're about to do will boil down to trying to argue that the optimal transport program in some sense is stable. At some level, both the primal and dual estimators are kind of taking some program and perturbing the input arguments to that program. And if we want to reason about it, we'll need to argue that somehow that program is stable. And we'll make a regularity assumption. It's sort of a strong one, but it's the one under which we know how to analyze this. So I will tell you what the assumption is, and then we'll inspect. So this is the assumption. We're going to hypothesize somehow, okay, we know that we've made enough assumptions to know that mu and nu are related. That is, if I think about uh, nu, I can always write it as the push forward of some phi zero. Uh, so mu push forward through grad phi zero is nu. So we've already made enough assumptions to ensure this. And our target is that we want to estimate this function. So the assumption that we'll make is that phi0 is not just convex, which we already know, but is rather strongly convex and smooth. And this will be the key assumption that will drive a lot of stuff. But maybe for now, let me just say, okay, well, if you're not used to thinking about it, you can assume for now that it's twice differentiable. It's not necessary to do so, and then the way you should interpret strong convexity and smoothness is that there's some upper bound on its Hessian and some lower bound on its Hessian, right? So this function is not just the convex, but its Hessian is upper and lower bounded, let's say by some lambda times the identity, and at most the identity over lambda. So there's some constant lambda such that this condition holds. So maybe the theme for today will be if you make this assumption that somehow the optimal transport program will have a lot of stability. It's it's a rather strong assumption, but there are some cases where we know that it holds, and I'll just briefly explain to you what those cases are. But let me again pause. If anyone has a question, just interrupt me. Otherwise, I will keep going for now. So okay, so there are a few cases where we know that this assumption holds, and this will allow us to think about whether it's a strong or weak assumption. So if mu and nu are supported on a bounded domain, on some bounded domain omega, and are bounded away from zero on that domain, and so they're strictly positive on that domain, and omega is a nice domain, so that is, it's a connected, uh, let's say, convex set with smooth boundaries. So you should think of omega as a nice convex set, and you have these two measures, and all you know is that they're bounded away from zero on this set. Then something called Caffarelli's regularity theory will tell you that, and I will tell you what this means, but it will tell you somehow that the Brenier potential corresponding to mu and nu will in fact satisfy this condition. Will tell you that the Brenier regularity condition. Okay. And maybe I will just say briefly what is going on here. So the way you should think about it, and we've remarked this before, that, okay, at least under some assumptions, you can interpret the optimal transport map via this change of variables equation. This change of variables equation is called the Monge-Ampere equation. So again, if you're used to thinking about PDEs, maybe you have come across this before, but it basically says that the measure mu and nu have to be related via change of variables formula. So that is mu, at least if you interpret things correctly, must look like nu of grad phi of x times some determinant of the Hessian of grad phi of x. So at least under appropriate assumptions, you can make sense of this expression. And now you can say, this is a PDE, right? So it tells you something. It's a second order PDE, but it's not a linear one. So if you compare it to something like Laplace's equation, which is a linear second order PDE, this is a non-linear one because of this determinant term sitting here. So if you replace the determinant by something like the trace, you would get some even more familiar class of PDEs. And so there is some regularity theory, which generally says, given a PDE and given some properties about the inputs of mu and nu, what can I conclude about the solution to the PDE? And this is, in this case, for this particular equation, it's called Caffarelli's regularity theory. So again, if it didn't make sense, don't worry about it. It's just saying people have studied the regularity properties of the OT map, and in particular of phi0, and there are conditions under which it is reasonable to assume that phi0 is smooth and strongly convex. And let me also say another case where we know this to be true is that when mu and nu are both smooth and strongly log concave.
Small question. So
Yeah,
the first point, that's just
yeah,
saying that if mu and nu both have a density, then this is just the change of variables, right?
yes. Yes, that part is correct.
And what is the Monge-Ampere theorem really saying that?
So I'm saying, okay, just imagine for a second that mu and nu are something, they have densities. Then you can view this equation as saying that, okay, roughly, you can ignore the thing here, but it's saying something like the determinant of the Hessian of phi zero is some function f, which we've assumed something about. We've said, okay, it's always positive. And now you can say, um, if I have a PDE, so this is a PDE of some sort, and I want to conclude that phi zero maybe satisfies some sort of regularity conditions. And so the Monge-Ampere equation is just the PDE, and then you can try to ask, when does this PDE have regular solutions?
No, so the preconditions are that if Brenier regularity is true, then this is true. Or
Yeah, so we're always making the assumptions of Brenier's theorem. That is, mu is an absolutely continuous measure, and you have bounded second moments. The Monge-Ampere equation holds. You have to be careful because I did not assume that the function is twice differentiable. So you have to interpret the Monge-Ampere equation carefully. But let's say you do, then yes, the Monge-Ampere equation is true under the assumptions of Brenier's theorem.
got it.
Okay, so let me keep going. The other case where we know that the the transport map is differentiable, or that the Brenier potential is smooth and strongly convex, is when you assume that the two densities are smooth and strongly log concave. So they don't have to be on a bounded support. All they have to do, they as long as they are log concave and smooth and strongly convex. Sorry, sorry, as long as they are strongly log concave and smooth, then the Brenier potential, in fact, satisfies this condition up here. Okay. In the statistical setting, though, you can just make the assumption that they are related by a strongly convex and smooth potential. And then the goal is just to try to estimate the gradient of this potential. And that's how we will work with these things. Okay. Question so far? Okay. So then let's try to get a handle on how one would analyze the
Hello.
dual. Yeah.
In omega, it was defined as connected convex set. So all convex sets are connected. So is there a need to emphasize on connectedness?
No, but somehow connectedness and smooth boundaries are the important things. You can get away in some cases with non-convex sets. So maybe, I don't know, yeah. Okay, you can, for now, the way I've written it, yeah, you can remove connected from it. Good. So let me now talk about stability bounds. So let's try to analyze the dual.
So I have a question.
Yeah.
The Brenier regularity theorem is saying that mu can be represented as the grad phi, sorry, push forward or grad phi naught of mu, that is nu. And then you're saying ki if these set of conditions hold, then that push forward equality holds, right?
No. So th okay, this you can take as always holding. We will always assume mu is absolutely continuous. I'm saying that if all of these additional conditions hold, it's
Right.
not just that it's the gradient of a convex function, but rather it's the gradient of a smooth and
Strongly
strongly
convex and
convex
smooth.
function.
I see. And for that, first possible set of conditions was mu nu supported on omega, and omega is convex with smooth boundaries. And then 2 is also another set of conditions, or
Yeah,
1
it's a
and 2 have
different
to
set of
work together.
conditions.
I see. All
No, no,
right.
there are two different set of conditions. There are two cases where we explicitly know how to certify that the map satisfies
All right. All
this.
right. Thank
They're
you.
disjoint conditions, or I mean, not necessarily disjoint, but there are two different ways of certifying it. Okay, so let's see how this goes. So let's kind of try to remember what we were trying to do. So let me define this semi-dual functional. So I will define something. For any potential phi, I can define this functional, which is the integral of phi under mu plus the integral of phi star under nu. Right? This is just some functional. And the question that we're somehow asking is, okay, if I perturb mu and nu a little bit, is it the case that the minimizer of this functional doesn't move too much? It'll turn out that one way to establish this is to say that this functional has quadratic growth. So this is what we will prove. So the functional has quadratic growth. This will imply for us what we want, that somehow the minimizer is stable in an appropriate sense. So I will tell you what I mean formally now. So we will show this, that if I look at this semi-dual at some potential phi versus the semi-dual at the true potential phi 0, right? So this is the minimizer. This is just some other function phi. And we will show that it's upper and lower bounded by something, which is it's upper and lower bounded by the distance between phi and phi 0 on the gradient scale. Okay, so this will be the L2 mu distance between them squared, and okay, so this is what I mean by quadratic growth, which is as I move away from the minimizer on the gradient scale, the function will grow appropriately. So in some intuitive sense, you should think of it as saying this functional S mu, S of phi grows quadratically around its minimizer.
Missing.
Okay. And this already somehow maybe explains why the semi-dual, at least under our assumptions, is a reasonable thing to try to minimize, right?
It's probably
So
lambda
there's some
missing.
sense in which minimizing it or making this difference small will force this distance to be small.
It's probably a lambda missing. Lambda.
Yeah, I'm going to drop all the lambdas. There are
Oh, okay,
lambdas
great, thanks.
all over the place. So when I use some squiggly less than, I just mean up to constants, and lambda I'll treat as a constant. Okay, so maybe it shouldn't have been so intuitive why optimizing this semi-dual thing was a good idea, but maybe once you have this quadratic growth, it seems to be a better idea. So somehow we're going to try to find a phi that makes this difference small, and then hopefully we will, as a result, conclude that we've estimated the transport map well. Okay, questions so far? Good. So let's maybe first do the statistical part. This is the easy part. So once you establish this lemma, trying to analyze something like ERM will turn out to be quite simple. So we'll do that first, at least under some assumptions. So this is the statistical piece. And then we'll come back and see why this lemma might be true. So what are we doing? So we are minimizing something like phi hat is the argmin over phi in some set of mu n nu n of phi. So this is our estimator. We're minimizing this functional over some collection. So in order to do this statistical analysis, I'll do it in the easiest case with a bunch of assumptions, and then I will point you to some papers that do it more generally. So here's the thing we're going to work with. I will call it transport map selection or potential selection. So this is just to get a flavor of what it is that people do. So we'll assume that there's some finite collection of potentials, and one of them actually shifts mu onto nu, and I want to identify which one or estimate one of them well. So this is what I'm going to give you. I'm going to give you some collection phi1 through phi m. You can think of M as fairly large, and the true potential phi zero is one of them. Again, you don't even need this assumption, but let's make it. And I will make the assumption that you're on a bounded domain. So, okay, as a consequence, one can maybe make the assumption that phi j, there's some bound on both phi j and its conjugate. Okay. Some of these assumptions can be easily relaxed, but let me just make them all so that it's easy to see what the basic analysis looks like. Okay, so I'm going to assume that all the potentials are bounded, that there's some finite collection of potentials. One of them actually pushes forward mu to nu. And is everyone okay so far? And okay, also that, sorry, there's one more important one, which is that all the potentials are smooth and strongly convex. All the candidate potentials are smooth and strongly convex. Okay, so let me also say here, sorry, in the lemma, you should also assume that phi is smooth and strongly convex. Okay. So we've made a bunch of strong assumptions. There are people who have written papers about weakening some of these assumptions, but let's say that this is the setting and we want to just analyze our estimator. And I will just try to explain how this quadratic growth condition gives you an analysis directly. So the starting point is just this basic inequality. So the basic inequality tells you that this is the standard way to analyze empirical risk minimization. It just says, okay, I know that phi hat, my estimator, minimizes the empirical risk. So its empirical risk has to be lower than any other candidate that I have. In particular, it has to be lower than phi zero. Right? So this is the basic inequality. It just says this quantity has to be at most the corresponding quantity in nu phi zero. Right? So my estimator, at least according to the empirical risk, has to be better than the truth. Okay? So now I can imagine the following thing. I can add and subtract some stuff. Right? So let's maybe start like this. So we can look at the quantity. So this is the population risk of my estimate phi hat versus the truth. Our lemma will give us some bound, a lower bound on this quantity, but we can also just keep going with it. So I'm just going to add and subtract some terms. Okay, so all I've done is added and subtracted this pair and this pair. But now we can start to see something. From our basic inequality, we know that if I put these two together, it forms something negative. So this one and this one together form something negative. So I can just drop them to get an upper bound. So in particular, we obtain that this is less than the following thing. And so in particular, it's less than twice the maximum difference between empirical and population risk, right? So this is max over J in 1 through M of the difference between Vj and this. Okay, so everyone roughly tracking so far. So this is maybe a standard analysis of empirical risk minimization. We've said as long as I can somehow uniformly bound the difference between the empirical version of my criterion and the population version of my criterion, then I get an analysis for the empirical risk minimization procedure. Let me pause for a second and see if, so we will now just quickly argue that this term is small, and we know that the the thing I started with is lower bounded by the error I cared about. So in particular, you will obtain the following guarantee that so this is a lower bound on this term will be less than 2 times this maximum thing, and we will argue that this is small in a second. So let me pause for a second. So this is just saying if you can show this quadratic growth condition and okay, at least you assume you're in a finite collection, then it is the case that you can analyze empirical risk minimization fairly straightforwardly. So all of the work goes into trying to show that this quadratic growth condition holds.
Is inequality the other way around? Like the
Which
thing you
one?
need, or maybe I'm stupid. So the last one, the very last
This
thing
one?
you wrote. Yeah.
So why is it the other way around?
No, but I need to upper bound the max, right?
Yeah, we will eventually upper bound the max. I haven't yet done it. I'm saying, okay, whatever the max is, it upper bounds the error that I care about. So
Okay.
eventually you will upper bound the max. So I haven't yet argued this, but I will
Okay.
in a
Okay.
second convince you that this is less than some epsilon for some appropriate epsilon.
So why is the left side the error we care about? Like, I didn't get the connection.
So this is the estimate of our transport map t hat, and this is the true transport map t0, and this is the distance between them according as integrated. So this was the risk that I said maybe
This
we
was the
should
risk.
care about.
Okay, great. No.
So the
Okay,
the
great.
quadratic growth condition is kind of telling us that this difference over here is lower bounded by the risk we care about.
Yeah.
And then from there, I'm saying it's a
Fair enough.
straightforward set of adding and subtracting stuff.
Also, why does the simple inequality hold? As in, because you're observing it under the measures, the empirical measures, right? So it
Yeah.
might as well be that the okay, never mind. I read it opposite. I'm so sorry.
Okay. That's fine. So, all right. So, if there aren't more questions, let me keep going for a second. So let me just quickly tell you, okay, how does one analyze the the term that somehow this is the main statistical term. It's just I want to know what is the maximum over my collection of potentials of empirical risk minus population risk. I've made enough assumptions that everything is bounded. So what is the empirical risk? It just looks for, so let's fix a phi. And roughly what are we asking? We're saying how far is this from the corresponding thing with empirical measures? Right? So what is this? This expression is just an average minus an expected value plus another average minus another expected value, right? So, and we've made some set of assumptions that say all of these functions are bounded. So there's just averages minus expected values of bounded functions. So Hoeffding's inequality with a union bound plus some union bound will tell you that the max, so with probability at least 1 minus delta. The max over J in this collection of the term I care about, which is the population risk minus empirical risk, is upper bounded by something which is roughly like square root of the bound that I've assumed. Actually, maybe times log m over delta divided by something like this. Okay, and then maybe there's a factor of 2 outside. So something like this is true. That is, the error in the transport map estimation will scale like it'll be less than something that roughly you should think of as log m divided by n. Okay, so all I'm saying is that once you've made at least this set of assumptions, the criterion, the semi-dual criterion, it's just an expected value. So the counterpart of it is just an average. And so you could say the average minus expected value by some standard set of inequalities will be small, at least if I give you enough samples. And then you combine it with a union bound and you obtain some statistical analysis which says, okay, if I'm selecting amongst m candidates, I should expect no worse than a log m over n rate. And if you want, you can do this now in a more fancy way. You can combine this with what are called chaining arguments and deal with infinite collections and so on. And you can also try to get faster rates if you exploit the strong convexity. So we only use the smoothness of this thing in this argument. If you also exploit the strong convexity part, then you can also get faster rates of convergence.
One small question.
Yeah.
The choice of norm for was infinity for the bound because of the max term.
Where did I write an infinity?
Bounded by, and the conjugates were bounded by B in the infinite
Yeah.
norm. Choice was
Yeah. Yeah, that's because I wanted to use Hoofding to make my life simpler. You could try to do something a bit cleverer. You could say, I don't know, it has a large bound but small variance. You could say it's sub-Gaussian in some appropriate sense and so on. So you can do many other things. But yeah, because I wanted to apply Hoofding, I assumed that they were bounded in L infinity. So I'm averaging a collection of bounded random variables. Other questions? Okay. So then let's do the meat of all of this, which is try to prove this quadratic growth. And hopefully I've convinced you that once you have this condition, there's some standard analysis of something like empirical risk minimization, which will imply what we want. We will get rates for transport map estimation once you have this assumption. So let's try to think about what, and this proof actually will give us some insight into what's going on. So we're looking at some term that looks like this difference. And we want to say that it's upper and lower bounded by something that looks like the gradient of phi minus the gradient of phi 0. Right? And just to remind you, what is the assumption we've made? Phi is smooth and strongly convex. Okay, so this is going to be our assumption in our lemma. Okay, so let's stare at this expression, and maybe the punchline will be that we'll rewrite this as a Bregman divergence, and then once you have this with a smooth and strongly convex function, and then once you know that it's a Bregman divergence, you get these upper and lower bounds. So let's do this. Looks like the integral of phi d mu plus the integral of phi star d mu minus the integral of phi 0 d mu minus the integral of phi 0 star d mu. So this is the term we're looking at. And now we will use some facts about Penshel conjugates that will be useful for us. So now let me write out what are the facts that I will use. So it's okay. So let me explain this slowly. So let's remember what defined phi star. Phi star of y was the supremum over x of x transpose y minus phi of x. And so this is what the conjugate is for a function. So from this, you can directly read off what's called Fenchell's inequality. So Fenchell's inequality just says phi star of y has to be bigger than x transpose y. So I'm just going to move it for any x and y. This is true. Okay. And you can ask, when does equality hold in Fenchell's inequality? And the following fact is true, that if y is the, so let's say it's a differentiable function, so y is grad phi of x, then equality holds. That is phi of x plus phi star of grad phi of x is in fact exactly equal to x transpose grad phi of x. Okay, so we can try to walk through some sort of proof of this, but maybe I can, for now, just take it as a fact about Fenchel conjugates that you can look up easily. So everyone okay with this? Okay. So then now let's go back to what we were trying to prove. So it'll be convenient to write. So we know that grad phi 0 pushes mu onto nu, right? So I can always write the integral of phi 0 star d mu as it's equal to the integral of phi 0 star of grad phi 0, say some point y d mu. So this is what it means. Sorry. Yeah. No, wait, sorry, I did something wrong, so let me fix it. Okay. So this is what I want to write, right? So the integral of phi 0 star under the measure nu can be written as, I take something from the measure mu, I push it through grad phi 0. Grad phi 0 pushes mu onto nu, and so it's equal to this quantity over here. Everyone good with this fact? So what does this mean? So our semi-dual with at the true potential phi 0 has a actually much simpler form. So that was, it was equal to the integral of phi 0 d mu plus the integral of phi 0 star d nu. But that is exactly the same as the integral of phi 0 of x plus phi 0 star of grad phi of x under the measure mu. And by Fenchell's equality, this is just equal to the integral of x dot grad phi 0 of x under the measure mu. Is everyone okay with this? Okay, so then let me keep going. So let's recall what we had before. We had S mu nu of our phi minus S mu nu of our phi 0. And so far we have said this is equal to the integral of phi d mu plus the integral of phi star d nu minus the integral of x dot grad phi 0 of x d nu. Yeah. Okay, and so let's do one more of these. So we also know that phi star actually, sorry. So we can write phi star of grad phi of x plus plus phi of x is equal to this is another one of Fenchel's equalities. So this is again the Fenchel equality. And so if I plug this in over here, I will obtain the following thing, that this looks like the integral. So I'll keep this term as it is. I will replace this term using this equality, and I will end up here that it looks like phi star okay, so I'm going to make a mistake with this algebra now. Okay, so let me just not do this algebra fully, but if you plug in this into this expression here, and you use this fact that the other, so that you have this term over here, you will end up, and you should trust me for now, with an expression that looks like this. Okay, so this is the difference between the semi-duals. And the key point is just that x itself is equal to grad phi 0 star of grad phi, or sorry, grad phi star of grad phi of x. And so this entire thing, this expression, so once I plug it in here, can be written in the following way. It's just the phi star Bregman divergence between two functions, phi 0, grad phi 0 and grad phi.
Yeah, and now we are done by strong convexity and strong smoothness. Yeah.
Exactly. Right, so this is, so yeah. Yeah, this turned out to be a bit harder to write than I thought it would be. So integral d mu. Right, so this is where we've arrived, that this difference of semi-duals is exactly, and this is a Bregman divergence. It's the integral of the Bregman divergence according to the function phi star between grad phi 0 and grad phi integrated. Right, so this difference of semi-duals exactly looks like a Bregman divergence integrated up. And let me, if you haven't seen Bregman divergences before, let me just draw you a picture so that you know what's going on. So there's some strongly convex function sitting here. This is phi star. It's the dual of phi. And we're using it somehow to measure distances between points. So there are these 2 points sitting here. This is grad phi 0 of x. And this is, let's say, grad phi of x. And we're defining the distance between them according to this function. So that is, we're saying, so a Bregman divergence basically defines, if you take these 2 points and say, what is the distance? It's the distance to the, so this will be defined. So you take the linear approximation of your convex function and then say the deficit of the linear approximation is measuring a notion of distance for you. So every strongly convex function can be used to measure distance. That would be called the Bregman divergence. And in this picture, it is this. This is the Bregman divergence between those 2 points that we wrote down. Okay, and what is the main punchline? if I assume the function is strongly convex and smooth, then the Bregman divergence is upper and lower bounded by some quadratic function, right? So it's just saying that the strong convexity and smoothness are saying the deficit to a linear function, the deficit of a linear function is exactly quadratic or behaves quadratically, right? So strong convexity and smoothness will exactly tell you that are upper and lower bounded by something that looks like V0 minus grad phi, the 2 norms squared. Right? So you have this pointwise characterization of this deficit. And then when you integrate it, you get exactly the claimed quadratic growth lemma up here.
How,
Okay, so
uh, how was x
yeah.
equal to grad phi star of grad phi of x?
Yeah, so this is also a general property of convex conjugates that yeah, grad phi star is the inverse map to grad phi. I don't know if you've seen the
So
analysis of mirror.
grad phi star is the Fenchel conjugate of grad phi.
No, phi star is the Fenchel conjugate of phi, but on the the gradient of the Fenchel conjugate is some sort of inverse map. So if you've seen the analysis of mirror descent, you've seen something like this before, but maybe you should imagine there's some primal space where things live, and grad phi kind of pushes you from here to there. And grad phi star is exactly, so if I take this as grad phi of x, and then the inverse map that pulls you back is the map grad phi star of y. Right? So they are in fact inverse maps of each other. Does that make sense?
Good.
Okay. All right. So maybe let's just pause for a second and think about what we've done. We've shown that the optimal transport program has some strong notion of stability, at least the semi-dual functional does. That is, it grows very nicely around its minimizer. And if you think about it, it should be a little bit surprising because the OT program and at least the original dual of the OT program are linear programs. So linear programs are notorious for not being stable in this sense. So in your maybe your head, you should have this picture that you have this polytope. You know that if I'm optimizing a linear function on a polytope, I end up at a vertex. And you can imagine if I push it slightly, I will jump to a different vertex. Right? So linear programs don't naturally exhibit this kind of stability. But what's going on in OT is that it's a linear program with a lot of structure. And in particular, your intuition about polytopes is kind of wrong because it's an infinite linear program with an infinite set of vertices and so on. So it is the case that in fact it can exhibit some very reasonable amount of stability. So high level, the OT program, at least under this Brenier regularity condition, is very stable. This semi-dual, for instance, is stable to perturbations of its input arguments. And now let me jump and tell you a little bit about how one analyzes uh, the primal estimators, and it'll be similar. We'll try to prove a stability bound. I won't prove it for you. I'll just state a stability bound, and then it will motivate what we'll talk about in the next lecture. Okay. Questions so far?
Questions?
No questions. Okay. So let me tell you about primal stability. So here's the high level question of what we were trying to answer, which is we defined, so let's think about plug-in estimators first. Okay, so here's the high level roadmap. We said let's define t hat to be the OT map between two measures mu hat and nu hat, where these were maybe constructed to be uh, density estimates of the original two measures mu and nu. And then there's a population counterpart, which is T0, which is the OT map between mu and nu. So the stability question, it's similar. When is it the case that t hat is close to T0? So in particular, maybe you would hope that if mu hat and mu are close and nu hat and nu are close, that t hat should be close to t0. And so the question then maybe is, okay, maybe mu hat should be close to mu and nu hat should be close to nu. And then we would hope that t hat would be close to t0. And the question is just, what is the right notion of distance, right? So in what distance do they have to be close? So the question is, does the OT program exhibit stability? And if so, to perturbations in what sense of its input arguments? And so I'll state a lemma now. It says the following: suppose mu and nu are related by this Brenier regularity condition. So that is, nu is equal to the push forward under some P0 of mu, and P0 is smooth and strongly convex. Then it'll turn out that for any mu hat and nu hat, they don't have to be absolutely continuous, they can be anything. It's the case that we can construct something. I'll tell you how we construct it. We can construct a t hat from mu hat and nu hat, such that the following thing will be true. The error of t hat as measured according to mu hat, so that is, let me say what this means. That will be upper bounded by the squared Wasserstein distance between mu hat and mu plus the squared Wasserstein distance between nu hat and nu. Okay, so this is an answer to this question. It says that the OT program in this form is stable to perturbations of its input arguments, and it's stable to perturbations in the Wasserstein sense. So as long as I can ensure that mu hat and mu are close, and nu hat are nu and nu are close in the Wasserstein sense, then I will obtain an estimate t hat. I'll tell you how in a second, which is close to t0, at least according to the measure mu hat. Okay, so let me pause for a second and see if there are questions, and then I'll tell you how t hat is constructed.
Is there an expectation there, or is it for all x?
No, so this is integrating over x. The expectation usually, so this holds for any, I mean, this holds deterministically, I guess. So usually when I write the risk, I write an expectation because t hat is random, and then we want to say something like the expected error is something. So the expectation is usually over the randomness in t hat, but here I'm saying it deterministically holds for any t hat that these conditions are true. Does that make sense? So you could, if you want, put an expectation here and some expectations on the right-hand side, but that's a strictly weaker statement.
Yeah, it makes sense.
Okay. Other questions? Okay, so maybe I didn't tell you how one constructs this map t hat. So let me tell you what it is. So remember, I didn't make any assumptions about mu hat and nu hat. So they don't have to be linked by a transport map. But Kantorovich tells me that there's always an optimal coupling, right? So there is always an optimal coupling gamma hat. And so we'll take the OT coupling gamma hat, and we'll construct a map from it. So this is sometimes called the barycentric projection of the map, of the coupling projection of gamma hat. But it's basically you project the coupling onto the space of maps. So that is, I will define t hat of x to be the conditional expectation of y given x, where x and y are drawn from gamma hat. Okay, so given any coupling, I can project it onto the space of maps. It's just take the, it could be potentially spreading out the y. I'll take the mean of all the y values for each x. Okay, so that defines a transport map. And this lemma tells you that that transport map will be close to T0 as long as mu hat and mu are close in the Wasserstein sense and nu hat and nu are close in the Wasserstein sense. Okay, and maybe this will set us up for the next lecture. So in the next lecture, we will talk about this question, which is just Wasserstein density estimation.
The coupling is on mu hat and nu hat, right?
Yes, gamma hat is a coupling of mu hat and nu hat, correct? Okay, so in the next class, we will talk about an even more classical problem, which is that of Wasserstein density estimation. So that is, how do we construct mu hat so that W2 squared, say, between mu hat and mu is small, or W1. So this is the goal for next time. And the implication will be, okay, once you understand how to solve that question, this lemma will tell you how to solve transport map estimation. And that's the powerful reduction that it gives you. It says, okay, transport map estimation seems like this hard abstract problem. You can get some results for it as long as you know how to estimate your densities well in the Wasserstein sense. Okay, let me stop here.
How do we know that this T hat X is asymptotically less than W2 mu hat mu and W2?
You mean, how do you prove this lemma?
Yeah, how do you prove this lemma?
Yeah, if I had been a bit more efficient, then I would have proved it for you, but maybe I'll tell you the high level thing. It roughly looks like you start with this Bregman divergence up here, and then you upper and lower bound it. The lower bound is exactly the same as what we saw, and it will give you some lower bound of this form. This is just the same lower bound argument that we made before. And then the upper bound involves some, yeah, you basically upper bound this Bregman divergence by using some sort of optimality conditions of the map, and then it'll end up looking this way. So I'm not going to prove it for you, but if I had some time, I would have. But it stems from staring at that Bregman divergence a little bit.
Got it. And one last thing, in the Bregman divergence, why, if you can go up there, why does showing that it's of this form immediately tell us that it is strongly convex? Or sorry, it grows. How does that tell us that it grows quadratically? Sorry, that's my question.
Yeah, so we made the assumption that phi star is smooth and strongly convex. And maybe I can walk through this. So suppose I take any phi that is smooth and strongly convex. I claim that this implies that the Bregman divergence grows quadratically. So what does that mean? So what is the Bregman divergence? Let's say d phi between 2 points x and y. It is equal to phi of x minus phi of y minus, let's say, grad phi of y dot transposed, uh, let's say x minus y, something. And strong convexity and smoothness. So this is roughly the some function minus its first order Taylor expansion. So this is roughly will behave like it's Hessian. So strong convexity and smoothness are maybe also usually phrased as saying whatever this deficit is upper bounded by the norm of x minus y squared. This is one characterization of strong convexity and smoothness. So it's less than lambda times this, and it's at least 1 over lambda times this.
Got it.
So yeah, so I mean, I don't know. One answer is you think of the Bregman divergence as roughly measuring it is something minus its linear approximation, which would behave like the Hessian of that function. The Hessian of the function you've assumed is upper and lower bounded, so it will behave this way.
Got it.
Hi. In barycentric projection, what is the expectation over?
Yeah, so I'm imagining I'm drawing a pair from the coupling and taking and I'm looking at this conditional expectation. So maybe I can try to explain it a bit better. So a coupling is just, so it's something like this, right? So if I fix one of the things, so I can look at the conditional distribution of this coupling. That is, I can say, what is gamma of y given some x equals little x? This is some distribution. If it were a single point, then you have a well-defined map. But what's going to usually happen is that it might split your atoms and move them around a little bit. So it doesn't define a map on its own, but I can say take the expected value of y for each value of x. And that's exactly what this is doing. And that defines a map for you.
So will that give you an OT map?
It will not. So it is not an OT map.
It's not OT between mu hat and nu hat.
No, so under these assumptions, there may not be any. So we haven't assumed anything about mu hat and nu hat, so there
If
may not
we-
be an OT map.
If we assume that it's all absolutely continuous and all of that, will this then be an OT map?
Yes, then this, so that is precisely what Brenier's theorem tells you. It tells you that this is a degenerate thing. It is just always equal to some map at x. Right? So this conditional expectation operation doesn't do anything. It's y is always equal to some t0 of x or t hat of x.
I see. So it tells you that the coupling will link every x to a degenerate y.
Yeah.
And so you get a unique map. I see.
Exactly. So yeah, you should think of the barycentric projection as saying when there is not a map, can I project it onto the space of maps? And this is the L2 projection of your coupling onto the space of maps.
If there are no further questions, let's thank the speaker.
Okay, thank you.